All right, welcome to lesson 3 of our first unit. We're going to be looking at specifically how radians lie on our unit circle. So you already had the radians showing up on that unit circle in our lesson 1, but just to really drive home where they hit and the exact values and their corresponding coordinates, because you are responsible for knowing that for your tests and for the provincial exam. You do not get a unit circle available to you. So we'll start with just the points that land exactly on the coordinates, which are, I'll use red just so they're more visible, here, 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 lying right on the axes. So this is at 0 radians. This is also 2 pi radians, okay? In terms of angle. Our coordinates, are going to be, well, x is 1, because remember the radius is 1, and we don't go up at all, so it's 0 there. But this is our angle, and these are our coordinates. I'll switch colors for the coordinates moving forward. I'll write the angles on the inside. Here is exactly 90 degrees. That's pi over 2 in terms of radians. And because we know that a whole distance around the circle is 2 pi, so half the distance around the circle is pi, and so half the distance between 0 and pi would be pi over 2. That's kind of how it subdivides. So here again, our coordinates, x is 0 because we haven't moved left or right, but y is 1. Oops, having all sorts of issues here. Okay, my coordinates for pi are going to be -1 because I'm left of my y-axis, and 0. And finally, we've gone pi plus another half a pi, so it's going to be 3 pi over 2. And that gets us to 0 and -1 because we're below the x-axis. So those are our first, and you know what, I'll just move these here now. 0 and 2 pi. Those are kind of a really good place to start in terms of reference angles, especially the 2 pi being the whole way around and pi being half, because we can kind of subdivide from there, and that'll work for all possible ones. So if we talk about 45 degrees, 45 degrees happens exactly halfway between 0 and 90, exactly halfway between 90 and 180, exactly halfway between 180 and 270, and halfway between 270 and 360. So with that, we've got 45 degrees, and that converts to, well, we've got pi divided into 4 pieces, so this is going to be pi over 4. And then it's going to be, this is still pi over 2. Okay, and then we've got, which could be also thought of as like 2 pi over 4, but I'm not going to relabel the coordinates just because it's already labeled in our previous one. Okay, and then we've got 3 pi over 4. This is 4 pi over 4, which simplifies to just pi. 5 pi over 4. 6 pi over 4, which is 3 pi over 2, 7 pi over 4, and this can still be 0, or 8 pi over 4, and again, that simplifies to, it's like too much like coordinates, 8 pi over 4, 2 pi. Again, so those ones in brackets are strictly on there to refer back to kind of as references and of our first example there. Our coordinates, you can look at your unit circle or you can remember them. Again, because it's 45 degrees, this makes a triangle where the 2 arms are the same length. So both my measurements should be the same, which is root 2 over 2. root 2 over 2. Now again, another way to be able to remember which one's positive and negative, we can look at our x and y axis and think about it in terms of that. But we can also think about it in terms of our acronym, all students take calculus. Bearing that in mind, sine is positive, and that's our y value. So negative root 2 over 2, root 2 over 2 here. We've got tan is positive here, which means sine and cos are negative. And finally, cosine is positive here, so that's root 2 over 2, but sine is negative, so y is negative. And again, I'm not going to label the points that I've already labeled in the previous one. For 30 as my radian measurements, kind of gets a little bit tricky going between here and the next one. So we've got 30 degrees. If we subdivided this into 30, we would go, oops, approximately here is 30, 60, 90, 120, 150, 180, go to 10, that's a little small for 30 degrees, 210, 240, 270, 300, 330, 360. So that's how we would subdivide it. And that looks great. So based on that and the dividing by 30, remembering that again, this is pi 0 and pi 2, 0 and 2 pi. If we look at how it's subdivided, well, it's divided into 6 pieces within a half. So 30 degrees is going to be pi over 6. So I don't even need to use my radian conversions. You totally can. You can use that ratio, but I can also do it visually here. So pi over 6, this would be 2 pi over 6, which would actually simplify to be instead pi over 3. This would be 3 pi over 3, or sorry, 3 pi over 6. How about I go through it like this? Just over 6's to start. 2 pi over 6. 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, if you want to think about it like that, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. But the tricky part is that these all reduce. We know that already. But actually 2 pi over 6 reduces to pi over 3. So it's not going to be an over 6 reference. Same with 4, same with 8, same with 10. They all reduce. So the only actual, and this kind of fits with the idea that I've mentioned before, where our reference angle is always measured from your x-axis. So really when we're talking about theta equals 30 as the associated values, we're going to be talking about 30 here, 30 here, 30 here, 30 here. We're not going to be talking about these other ones. Those are going to be known as like our 60s related angles, because this distance is actually 60 degrees. It's 2/30, right? So we're not going to work with those in this diagram. So if you want to like ignore them, highlight only the ones that matter for this one. Okay, it's going to be 5 pi over 6, pi over 6, 7 pi over 6, and 11 pi over 6. And our coordinates are, well, our x is going to be longer than our y in terms of visual representation, if you remember the values. So if x is longer, that's the square root of 3 over 2, and the y value is 1/2. Again, using our all students take calculus acronym, here sign should be positive, so negative cosine, positive sine, both are negative down here. And only x is positive here with cosine. So those are all our radian angles that are associated with 30 degrees. So pi over 6 is our 30-degree value, whereas pi over 4 we saw is our reference angle for up here. Okay, and like we saw up here, I'm going to skip through drawing those 30s again. I go 60, 120, it's a little too close to 45s. 60, 120, 180, and then 240, and 300. And then obviously making it all the way back to 0. So again, if we look, remember that this is pi from 0, then we're dealing with divided in 3, so that's my denominator, and that's my reference angle for 60 degrees is going to be pi over 3, because half a circle gets divided in 3 for 60 degrees. Based on that, I can label my angles as pi over 3. This would be 2 pi over 3. And again, we see that when we look up here, 2 pi over 6 would reduce. 2/6 is 1/3, and that's what we're seeing here. Okay. Here we've got 3 pi over 3 is another way of thinking about it. And that'll kind of come in handy later when we start talking about identities in our third unit. This would be 4 pi over 3, 5 pi over 3, and again, 6 pi over 3 would reduce to 2 pi. So those are radian angles that you'll want to kind of lock in and associate with that 60-degree reference. Pi over 3 is 60 degrees, if you remember nothing else. And so then working with that 60-degree reference angle, we've got a shorter x and a longer y here, so that's where those two values switch from our previous diagram. Here again, all students take calculus, quadrant 2. We've got our y value stays positive, but our x value becomes negative. Both are negative down here. And only the x is positive here. Now, before we move on, just a quick note. Writing it as -1/2 is equal to writing it as -1/2. So whichever way makes more sense to you, if you see one or the other written, that's totally fine. They mean the same thing. I just have a predisposition, since we do most of our math in the numerator, I usually attach it to my numerator. So using all that information above and using those exact values, those set values, we have a word problem, and we can actually try and apply our understanding of radians and those set values to figure this out. So an approximate model of the motion of the International Space Station is that it travels at a speed of 27,600 kilometers an hour in a circular orbit at an altitude of 400 kilometers. So that's 400 kilometers above the surface of the Earth. The radius of the Earth is approximately 6,400 kilometers or 6,400 kilometers. A says visualize the line segment joining the space station to the center of the Earth to the nearest tenth of a radian. Okay, and because they tell us exactly how much, that helps me with my decimal place. Through which angle will the segment have rotated after 40 minutes? So this is an application of our previous lesson, along with some understanding of speed. So I like pictures, just personally. This is Earth. And this is my space station. Okay, and it's traveling in a circular pattern. Work with me here, imagining it. Okay, from the center of Earth to here is 6,400 kilometers. Then we have an additional distance of 400 kilometers. And it's traveling around Earth at 27,600 kilometers per hour. So in 40 minutes, well, we're working in per hour here. So the first thing I want to do is convert minutes to hours. So 40 minutes is equal to 2/3 of an hour. Right, because we're dividing by 60. Once I know that, I can actually find the distance traveled. And that's going to be my arc length, my S value. So I can figure that out by multiplying time by my speed. So 27,600 times 2/3, which gives me an arc length of 18,400 kilometers. So that's great. That's a really far distance. Now I'm going to go back to that formula that I had here from last lesson. I'm going to use that to fill in 18,400 equals R, which is going to be 6,800 theta. And again, theta is in radians. All I need to do is divide by 6,800 on both sides. And that's going to give me theta. When I punch that into my calculator, that gives me 2.7 radians. So that would be my answer to A. To the nearest 100 kilometers, what is the straight line distance between the initial and final position of the space station? So this becomes a little bit trickier. So it's traveled. Again, I'm going to draw a picture. It's gone from here to here, and so if I draw an actual line to it, I don't know that it's necessarily a right angle triangle, but I know that this is the center of the Earth. This was the initial position. This is the final position. So, whereas this is 6,800 kilometers. This is also 6,800 kilometers. And this angle here is 2.7 rads. From here, I can use my cosine law way back from grade 11 to figure out that space. So if we go by that law, be the equation I'm using. No, C unfortunately is actually A based on my equation. So I've got A squared, which is now C squared. And then we've got 680 squared plus 680 squared, or not 680, sorry, 6,800 minus 2 times 6,800 squared again, because it's the same thing multiplied by itself. Cos angle A is 2.7 rads. So this is where you're going to want to check on your calculator. Make sure it's in rads instead of degrees. You can do that usually under mode, or sometimes there's an actual button for like degrees, rads, etc. So figure that out before you start punching anything in, because you're going to punch all of this into your calculator to get your answer. All right, so in order to be able to punch this in, I'm just going to use my calculator on my screen here, so bear with me as it loads. You want to be really careful that you're punching in everything exactly as you've written it down. So as mine comes up, I've already been working on it here, so I can just show you what I've typed in. So I've got 6,800 squared plus 6,800 squared minus 2 times 6,800 squared cos 2.7, and I hit equals, and this is the value I get. Now, when I go back to my screen here, what we're seeing is that we've got c squared equals all of that. Now, I'm not going to write that whole number out because I am just not interested in spending that time there. So what I'm going to do is I'm going to take the square root of all of this in order to eliminate that square there. And so what I'm going to do on my calculator, so once I've found that value, I'm just going to go second function square root of my answer, and that's going to give me 13,269 point whatever. But the question asks us to round to the nearest 100, so really my answer is going to be 13,300 kilometers. And there we go. That's my answer. So a question like that where we have to recall like our cosine law is less likely to going to show up on our provincial exam, but can happen, and so it's good to still be familiar with those. Don't let them slip out of your brain quite yet. Looking at example 2, we're going to be looking at a little bit more of the like exact value and understanding of revolutions, going back to that very first lesson. So in example 2a, we've got point P is at -4 and +3. And again, we just have to kind of sketch it out. It's the terminal point of angle theta. So theta is, again, always measured from 0 degrees. In standard position, to the nearest tenth of a radian, so again, they're telling us where to round it to, determine possible values for theta in the domain of -2 pi to +2 pi. So in grade 11, you would have been asked a similar question for -360 degrees to +360 degrees. Okay, it's asking the same thing. So you're not allowed to go past -360. You're not allowed to go past +360. Same thing here, except in terms of radians. So I'm not going to be allowed to go past 1 revolution going this direction from 0, and I'm not going to be allowed to go past 1 revolution going the clockwise direction from 0. So how do we do this? Well, in terms of tackling it, there's a few different ways. We've got negative, not negative. We've got 3 as our vertical and negative 4 is our horizontal. And we can call this theta r. It's our reference angle. Because we know that sine is positive here, but we can always work with a reference angle, and that will always be a positive small angle, always measuring from our x-axis. So that's what I'm going to do here. I'm going to go, okay, well, this is my opposite side relative to my reference angle. This is my adjacent side. And so what we're going to do is we're going to figure out, okay, well, what is my reference angle? And with opposite and adjacent, I can use tan. So tan of theta r equals 3 over 4. And I don't need to use that negative anymore because I'm working with a reference angle, which typically lies in quadrant 1. So I can drop the negative, and I'm allowed to do that. So in this case, if I want to find my reference angle, I can go tan inverse of 3/4, and that will get me some value. So again, bear with me. I've got second function tan 3/4, and again, oops. Oof, it's not liking me today. That's going to give me 0.64 as my reference angle, or even just 0.6 since it's asking for the nearest radian. But that's my reference angle. That's not my actual angle. So remembering that my actual angle is measuring from my x-axis. So here is pi. We're going to be measuring backwards from pi. So I'm going to go, my actual theta is going to be pi minus 0.6 for quadrant 2. And so again, we'll use the calculator. I hate that I have to press the second function for that. 0.6 equals, so 2.5 is going to be my answer. That's great. And that's going to be my positive value. So between 0 and positive 2 pi, that is my solution. But I also need to be able to measure, so that's theta going this direction, but I also need to be able to measure my negative angle because that fits within the parameters of negative 2 pi being my minimum because I can go past it to negative 2 pi. So in that case, what I'm going to do is I'm going to go, well, that's negative. This is considered negative pi, so I would add my reference angle. So go pi for negative pi, and then additionally subtract 0.6, whichever way you want to think about it. Or you could think about it as it's all negative, but it's pi plus 0.6, whichever one makes the most sense to you. I typically would think about it like this, but others would prefer the negative pi minus 0.6 still, in which case it gets me ooh, what happened there? .3. So negative 3.7. Radians would be my other option. And so those would be my two answers. So I know that one's a little tricky, wrapping our head around the idea that we can have more than one answer for a question based on the fact that we have a wider range of domain is something that we're going to have to get comfortable with and do more examples of. So conversely, if we're working with the given cotangent theta equals -2. So again, right off the hop, I'm going to notice that it's cotangent. I hate cotangent. I hate those reciprocal ones. So if cotangent theta equals -2, I'm automatically going to start thinking in my head, okay, well then tangent of theta equals -1/2. And I'm going to be planning to work with this. It says determine the values for theta in the domain from -2 pi to +2 pi. So we are given ample opportunities here because we've got a few different places this can exist. To start with, if we use our acronym, all students take calculus, tangent is going to be negative in more than one place. So we're going to have a potential for an angle here and angle here in quadrants 2 and 4. So we will potentially have a point here and a point here. But in both cases, our reference angle is the same. So that's why figuring out a reference angle is nice to start with, because that allows you to kind of work within any quadrant, as long as you remember where you're measuring from. So how we can do this is our reference angle, just kind of as a note, is always in quadrant 1. Therefore, our ratios are always positive. And that's because all ratios are positive in quadrant 1. So when I find my reference angle, I can do it by doing tan inverse of not just -1/2, but just 1/2. Zero 0.4635 radians is my reference angle. So from there, I can find my actual angle of, we'll call this 0.1 and 0.2, just for, so theta, so when I'm working with 0.1, theta could be pi minus my reference angle, because again I'm measuring backwards from pi towards 0. Which gives me 2.67795. But again, I'm allowed to go within my negative values as well. So if I'm measuring from here, it's going to be negative pi and a little bit. So again, I like doing it with the negative out in front and then just thinking in terms of positives. So I get negative 3.60524. So those are my possible values for 0.1. But I can also have possible theta values for 0.2. So I'm going to work over just to the right, 0.2. I'm going to follow the exact same process, except I'm measuring from 2 pi and working my way downwards towards my terminal arm. So in this case, for my positive theta, I'm going to take 2 pi minus my reference angle, 0.46365. I'm going to solve for that. That gets me 5.81954 radians. So again, that's my positive value. But I could work from a negative perspective as well, in which case it would just be from 0 measuring to this terminal arm. So that's probably the nicest one to work with, because that would be just negative 0.4. Sorry, ahead of myself, 46365 radians. So we've got 4 answers for this question. So you have to be careful when we start getting no further restrictions in terms of which quadrant it's in, that we can usually end up in 2 quadrants, whether it's positive, in which case for the tangent that would be quadrants 1 and 3, or if it's negative, like this example where we ended up in quadrants 2 and 4. So those are some tricky questions. I hope that that makes sense. Again, please ask all the questions if you're not sure about something, and I'm more than happy to help. There is some homework for this lesson, just some practice with the exact values of the unit circle in one PDF, and then I'm hoping to find something to give you a little bit more practice with these last two kinds of examples, and especially this example 2 style of question, since you will probably see something again along the lines of these in the provincial exam.